Alright, now we're looking at exact differential equations. So I've already written a little bit of stuff here, so let's just talk about it. First of all, you want an exact differential equation to have this form: some function of x and y with a dx plus some other function of x and y with a dy all equal to 0. You notice that if this is a plus, then this is the same thing as writing dx dy is equal to negative m over n. And then we say that this function, if you have a function in this form, we say that it's exact if and only if the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. Notice n up here has a dy, but we're taking partial derivative with respect to x, and the m has a dx, but we're taking the partial derivative with respect to y. Kind of looks a little backwards, but that's just the way that we do it. Also, this only works if this is a plus sign. If you have a minus sign, don't even look at this. That won't even make any sense. This has to be a plus sign for this to work. So if you have a minus here and you want to see if it's exact, change this to a plus and multiply all of this stuff by minus 1. Okay, so the way that we solve one of these, if we have this form and this is true, then we know it's exact. So then what we can do is we have a solution. Our solution is equal to this function. We're going to call it phi of xy. Some other function of xy. First of all, this is also equal to a constant, and it has the special properties. We can write this in a different color. D dx of phi is equal to this function m of xy. And it also has a special property where d dy of phi is equal to n. And that was a function of x and y. Alright, and we also said that phi of xy is also equal to c. So if we want to go ahead and solve for what our solution is, there's two ways we can do it, so I'll do both of them. We'll say that phi of xy is going to be equal to the integral of m, and then we can just keep writing these m, this function of x and y. Plus some other function that we don't know, we'll call it g of y. And sorry, there was a dx here. Now, in order to find this g of y, what we need to do is we need to take the partial derivative with respect to y of both sides of the equation. So we can write this, we'll say dy of phi is equal to dy of each term. So we have the integral of m of xy, that was dx. Now when we take the partial derivative of g of y with respect to y, that's just, there is only y's and constants in this function, so that's just taking its derivative. So we will say this is equal to g prime of y. Now we still don't know what this is, and we said that the partial derivative of phi with respect to y is equal to n of xy. So this is all going to be equal to n of the function of x and y that we called n. And this was given to us in the original equation. So now what we're going to do is we'll be able to find out what this is. We can take the integral of m and then take its partial derivative. We know what n is, so then we're just going to be left with this one term here that we can easily solve because we'll just have to match up and make the left side equal to the right side. Then once we get g prime of y, take its antiderivative to get g of y, and then we'll have the solution if we plug it back into here. The solution to our differential equation would be the integral of m plus this function that we found, gy. Now the other way that we can do this is, here we'll change colors. Instead of using m, we can do the opposite. So we can say that phi, which is a function of xy, which is our solution, is equal to the integral of n, which was a function of x and y, and this was dy, plus some other function, let's call it h of x. So this will be our solution to the differential equation. Then all we have to do is do the same, but kind of the opposite. So we'll take partial derivative with respect to x. d dx of phi is going to equal to, we'll take partial derivative of everything on this side. So we would have integral of n is a function of x and y, dy. So I'll take the partial derivative of this stuff with respect to x, plus the partial derivative of this stuff with respect to x. But again, this is only a function of x, so that just becomes h prime of x. And if we're taking the partial derivative of phi with respect to x, that means it's all equal to m of x, y. All right, so again, we can easily solve this because we will be given this function n of xy in the problem. Take its integral, then take its partial derivative. We know what m is, and then again, just fill in the blanks, solve for h prime at x, take its antiderivative to get h of x, and then we have this expression here that is the solution to the differential equation, and this statement would be exactly the same as the statement because it is phi of xy. There's just two different ways to go about it. Alright, hopefully that's not confusing. Join me in the next video and we'll actually go over a real example and you guys will see how this works.